Okay, in this lecture, we are going to take a digression into some mathematics called about the cubic equation. And the reason is because our problems involve solving a cubic equation, specifically all of these guys. Every one of these is basically a cubic equation. Even this one here that looks like a quartic equation, it's really cubic because you see all the terms are, well, it has one root of 0, which is obvious, and then the remaining roots are the result of a cubic equation. We are going to be attacking these cubic equations pretty aggressively in different ways. This one here is one that we're going to focus on a little bit in this lecture. And we're going to understand this guy, and we're going to understand this guy in great detail. But this is basically an algebra lecture, right? We just want to be comfortable with these solutions. The reason, if you go back to the paper that I'm citing, this paper by Kostic I, it's the one that I read to learn about this stuff the first time. I read several papers, of which I all cite in the book Why Does It Move, and I also have them available for the Patreons for the patrons on the Patreon site. But this is the paper, and it's easy to find. I've left it up here so you can see how to find it in the archive. And it's called Analytical Time-like Geodesics in a Schwarzschild Spacetime. And this paper is basically does all of the math that I'm going to be duplicating in this lecture. But I just go a bit deeper, and I explain things a little bit more deeply because it's a high-level paper. It does a lot of work. I got to say, Kostic jammed a lot of really good knowledge in this paper. It's a fantastic paper. But I'm just since I have all the time in the world and he doesn't have all the space in the world for these publications, I'm going to try to explain certain things in particular depth. And one of those things he talks about, and this is from his paper, all of this is from his paper, is there comes a point where he talks about how to solve a cubic equation. And this is the part he gives right here. And we're going to sort of flush this out a little bit. We're not going to derive the cubic equation from first principles. You can do that, but that's a massive algebra lesson, and it's a combination of algebra and history. But the purpose of this lecture is to sort of attack this guy right here, this cubic equation right here, and sort of understand the feeling of how this is done. So whenever you see we're talking about the roots of a cubic, you've been through the exercise, you've made yourself sort of qualified to say, oh, I understand. There's going to be 3 real roots, and in a certain circumstance there'll be 3 real roots, and this is the first root, the second root, and the third root. All right, so let's begin. So we will begin with a trivial cubic equation. Trivial in the sense that it's easy to look at, nice integer roots. But when you expand these 3 roots, 1, 2, and 3, you end up with this polynomial. And that polynomial is our cubic equation with 3 real roots. Now, the other possibility, of course, is 1 real and 1 complex root. And that would be this expression right here. This cubic equation is designed to have a complex root of 2 plus or minus I and 1 real root. And you can multiply this out as I just did to make sure I got it right. And this is that expression. This is the final polynomial in this exemplar case. So we're going to have 2 polynomials, 2 cubic equations. One we know has a real root, which I'll call R1, and then 2 complex roots, which I'll call B and B conjugate. And this one has 3 real roots, R1, R2, and R3. Because I need commas here. Now, there are a few facts. I'm just going to be telling you facts about the cubic equation that ultimately, if you really want to dig into, you'll have to learn separately. But there are some relationships between the roots of cubic equations that we need to know. In particular, we have these 3 relationships. The first is that the sum of the roots equals the coefficient of the second degree of the polynomial to the coefficient of the third degree of the polynomial. That's what A2 and A3 are. I should write that down. Right here it is. If this is your cubic polynomial, the sum of the roots is this particular ratio of the coefficients. And then this is, I guess I'll call it the sum of the symmetric product. Well, the symmetric sum where you know, if you interchange any of these two, nothing happens. But that symmetric sum equals this ratio, the linear term over the cubic term. This is the quadratic term over the cubic term. And then the product of all three roots is the constant term over the cubic term. And these are called Vieta's root formulas. I think it's Vieta. I think there's an accent there. Italian guy. He did this in the 1500s. He figured this out. Now, in our particular case, you can immediately calculate the value of these things. A2, for example, in the case of three real roots, A2 is 6, minus 6 is 6, A3 is 1, so they add up to 6. Then what's nice is A3 is 1 in all our cases here, so this just equals the opposite of the constant term, so this product is going to be 5, and this product, this sum of these products is going to be 11. When I said 5 here, well, this works for both cases. So I don't have to say. So the product of the three roots here is also minus A0 over A3. It's just R2 and R3 are replaced by B and B conjugate. We could actually check that right here. For this polynomial, the first root is 1, the second root is 2 plus I, the third root is 2 minus I, and if you multiply this out, you get 4 minus I squared, so it's 4 plus 1, which is 5, which is the opposite of minus 5, because A3 is 1. So these work for real and complex roots. You just have to replace R2 is B, and R3 is B conjugate, right? That's all you would have to do. But these root formulas, this is one thing you need to remember for cubic equations, right? This is just an expression that somebody figured out that is pretty important. All right, so now to attack the cubic equation itself. All right, so let's begin with the one that has three real roots. We look at, I'm going to teach you the procedure, right? The procedure. So we start with, calculating two intermediate factors that are very important. One is called Q and one is called R. These are just some intermediate numbers that we need to know. And Q is 3 times the linear factor minus the square of the quadratic factor over 9. R is a little bit longer. It's 9 times the quadratic factor, 9 times the product of the quadratic factor times the linear factor minus 27, the product of the linear factor, 27 times the linear factor minus 2 times the square of the quadratic factor. Then the next important number is D, which is the discriminant. It's Q cubed plus R squared. And we treat the discriminant, the usefulness of the discriminant here is just like it is for the quadratic equation. If you have D greater than 0, D less than 0, and D equal to 0, it tells you different things about the roots. And in our particular case, the way we understand our discriminant, clearly if it's going to, the only way it can be less than 0 is if Q cubed is less than 0. And if it's less than 0, we have 3 real roots. If it's greater than 0, we have 1 real and 1 complex root. Well, I guess 2 complex roots. And if it's equal to 0, then we have we have 1 real and then 1 double root. I guess that's the way it works. And then next is the intermediate value psi, which is actually an angle. And psi is the inverse cosine of r over the square root of minus q cubed. Now remember, this analysis is we're going to apply to the cubic equations that have 3 real roots, right? So this will only work if we are in the d less than 0 case where q cubed is definitely negative, because that, of course, is always positive. And so minus q cubed goes in there and is negative. So now, if we calculated these numbers for our particular equation as an example, what would we get? So for our expression, the values q is minus 1/3, r actually is 0, d is minus 127, the discriminant, which is less than 0, as we expect. And this angle psi, that's so important, that's part of our initial series of intermediate values. That's the cosine of, well, since r is 0, it's the inverse cosine of 0, which is pi over 2. Then from this, we have formulas for the roots. The formula for the first root is 2 times the square root of the opposite of this intermediate value q, which we know will be a positive number because we're dealing with the 3 real root condition where d is less than 0, and the only way d can be less than 0 is if q is less than 0. So that'll be positive, times the cosine of psi over 3 minus the quadratic coefficient over 3. And in our case, this number equals, which equals this, 2 times the square root of 1/3 times the cosine of pi over 6 plus 6 over 3. The cosine of pi over 6 is root 3 over 2, so everything actually cancels here to 1. 6 over 3 is 2, so it's 1 plus 2, which equals 3. So one of the roots is 3, and of course, by the way we designed this this equation, we know, let's see, where did I do it? We know that we have in fact built one of the roots to be 3. So we found actually the largest root. So this is the formula for our first root. Then our second root formula is this, right? The second root is basically the same thing up front. The only difference is the psi over 3 becomes psi plus 4 pi over 3, and everything else is the same. So this will end up being cosine of I guess if I did it, it would be 5 pi over 6. And it turns out 5 pi over 6 is negative, right? This becomes a negative sign. And that becomes a negative 1 plus 2. So this guy ends up equaling 1. And the last one of these, E3, is going to be 2 times the square root of minus q, and then it's the cosine of psi plus 2 pi over 3 minus a2 over 3. And in that case, this will be not 5 pi, but it will be 3 pi. And the cosine of 3 pi over 6 is the cosine of pi over 2, which is 0. So this whole thing goes away, and you just have 2. So it equals 2. And there's our 3 roots, 1, 2, and 3. So if you have a discriminant that's less than 0, the cubic equation comes down to these 3 expressions. These are the 3 roots for the cubic equation. And we usually like to order them. So 1 is the largest root, and 2 is the second largest, and 3 is the third largest. But here, the way it came out, it didn't come out that way necessarily. But we will reorder the roots later. But this only works for when you have 3 real roots. And notice that everything here is totally in terms of the coefficients of the original polynomial equation, right? All we have is A3, A2, A1, and A0. A3, this is total generality because we just divide through by A3 and get a different A2, A1, and A0, and our formula works just fine. And so everything's in terms of the coefficients, and you end up with the 3 real roots. Now let's examine the case when you have 1 real and 1 complex root. So this is our cubic equation that we know has 2 complex roots that we're going to study. The first step into solving those is, well, first we can calculate Q and R and D. So for this problem, they are 2/9, minus 10/27, and 4/27. So D is positive, and of course Q you can't say anything distinct about Q just because D is positive. If D was negative, you could definitely assert Q would be less than 0. But in this case, it's positive, R is negative, and D is positive. So that puts us in the condition of one real and one complex pair of roots. So because we know that, we know we can't use the other method. The other method will fail for that, and you can tell it'll fail because it always requires, in full generality, Q to be negative, which will only always be guaranteed to be true in the case of 3 real roots. So to proceed in this case, we're going to do another intermediate step that's a little bit more complicated, and we're going to take the original equation and convert it into a depressed form. Depressed form. And that substitution, there's a substitution for x that turns this into a depressed form. And let me show you what the substitution is. The substitution is x equals y minus a2 over 3a3. And for any cubic equation, this will turn any cubic equation into a depressed cubic equation. And the coefficients of the depressed cubic equation are the following coefficients. It's a bit of a mess, but if you make this substitution into our quadratic or our cubic equation, meaning you replace x with y minus a2 over 3a3, where the a3 is 1, a2 is minus 5, a1 is 9, and a0 is minus 5. If you make that substitution, you'll discover 100% of the time you end up with this cubic equation. What makes this cubic equation depressed is, notice you have a cubic term in y, a linear term in y, and a constant term, but no quadratic term. There's no quadratic term, and that's why it's depressed. And the results for our particular version are as follows. Oops. This is squared, not cubed. This is squared. The cubed is a2 cubed is on this linear term. A2 squared is in. A2 cubed is in the constant term. A2 squared is in the linear term. So for ours, it ends up being this guy. Y cubed plus 2/3 y plus 20/27 equals 0. And you'll see there's no y squared term. And that's the depressed cubic form. So once you get it in the depressed cubic form, then we will rename the general depressed cubic form. Notice there's also no coefficient in front of the y, right? The y will always, the reason there's no coefficient for us in front of the y is because a3 for us is 1, right? In general, you will get a coefficient in front of the y, but the result is still the depressed cubic form. So now I will rewrite this expression just so I can write down the formula conveniently, because now that we have a depressed cubic form, we can write an explicit formula for the roots of the depressed cubic form. We can write an explicit form of the roots for this thing in general, but we have to start with the depressed cubic form. So if we have a general depressed cubic, then the linear term we'll call f and the constant term we'll call g. And the presumption will be that there is no factor up front, right? So we will divide through. So you have just a 1 here and f and g. And once you have that, we create 2 new intermediate values. These new intermediate values are called I1 and I2, and they're just constructed out of the coefficients of the depressed cubic form, g and f. And the only difference between the two is the sign of this guy in the middle. And notice it's a cube root. So for our problem, these results for I1 and I2 are minus 1/3 plus root 3 over 3 and minus 1/3 minus root 3 over 3. And you got to wrestle with it a little bit because the f and g, taking it to the square over 4, you end up with an expression in here that doesn't obviously generate to this, but you can work it into these, and for our particular case, you can work it into this relatively simple form. And what's nice is once you have it in that form, the answer is very quick to come. The first root, which I'll call R1, is simply the sum of I1 and I2. And that's going to be the real one. So you can tell that this, this part here, this part and that part will cancel, and so the sum of those two is going is the first root, and that equals for our case here minus 2/3. And then the next root is these complex pairs, but b is going to be I1 plus I2 divided by 2, oops, negative sign in the front of this whole thing. So I'll just go times -1. And then it is plus I times the square root of 3/2 times I1 minus I2. And then, of course, B conjugate is the same thing, but you will have this plus replaced by a minus. So what I'll do is I'll go B, well, let's see, I should do B conjugate is this plus minus. How about that? Now in our case, for our result, the complex conjugate numbers are 2/3 plus or minus I. Everything cancels nicely. Of course, it's by design, right? We built polynomials that had relatively simple roots. But 2/3 plus or minus I and minus 2/3 is not the roots of our original polynomial, remember. This is the roots of the depressed polynomial, this guy right here. So that's different, right? Now what we have to do is that's the roots for here. Now we have to calculate x through this expression here. So in other words, we have to do the substitution in reverse. X equals y minus a2 over 3a3. So if we do this for the real one first, we get x equals minus 2/3 minus, let's see, I put the minus sign up there, minus a2 over 3a3. Now a2 was minus 5 minus 5 over 3, which is minus 2/3 plus 5/3, which equals 3/3, which equals 1. Okay, and 1, when we constructed this guy from the beginning, you see that 1 was the real factor. Our other two factors better show up to be 2 plus I and 2 minus I. So we'll go back here to this screen and we'll make this substitution now for 2/3 plus minus I. So the substitution we have to deal with is y minus a2 over 3a3, which is y plus 5/3. And then I think we had, what was our final result for the roots? It was 2/3 plus minus I. So that's going to be 2/3 plus minus I plus 5/3, which is going to be well, that's not right. Something's wrong. I did something wrong, and I can almost guess what it was. If you go back here, you see it's I1 plus I2 divided by 2. I just took I1 plus I2 and said minus 2/3, but I forgot to divide by 2. So if you divide by 2, you get a 1 here, and this ends up being 1/3 plus 1 I, right? So we correct that, and we get this to be 1/3, and then we end up with 6/3 plus or minus I, which is 2 plus or minus I, which is what we know to be the answer. So now we've demonstrated how to calculate the roots of this original expression. We looked at it, we looked at this cubic, we checked Q, we checked R, we checked the discriminant. We found that the discriminant implied that there were a complex pair of roots. Once we did that, we said, okay, it's time to convert it to a depressed form. Once we converted it to the depressed form using these formulas, which are very kind of a mess to derive, but you can go through the analysis of the cubic equation and see how it's done. It's essentially done by factoring out the real root, leaving behind a quadratic, and then using the quadratic, solving the quadratic. using the quadratic equation. And so then this guy here, we created this, and then we use these two formulas here for I1 and I2, and then we have these root formulas based on I1 and I2 for the complex pair and the real pair. And then we were also able to attack the expression if when we had analyzed the original polynomial, Q, R, and D were such that we had 3 real roots, we would have used this method, which was a bit of a trigonometric method. Now, but I should say something about the trigonometric method there's other ways of looking at this that are completely equivalent, but you end up with an arctangent here instead of an arc cosine. I'm not quite sure why you would prefer one over the other, but there is another method, and some of the papers we cite actually use the other appeared method. But they are exactly equivalent, and if you just work through trigonometric identities, you can find how an arctangent and an arc cosine are actually the same in this process. In fact, let's go ahead and back to Kostic's paper and see how he handles it. You'll notice that in Kostic's paper, he has slightly different definitions of things. Here's this arctangent. It's 2 times the arctangent of minus d over alpha plus beta cubed. And inside the paper, you will see how alpha and beta cubed are related to q and r, like we had it. And all of these, and through this, you end up with square root of minus q, right, which appears here. So it's doesn't look exactly like what we have done, and he ultimately chooses this arctan definition, which is entirely equivalent. If you make all the substitutions between our approach and the approach in Kostic, you'll see that they're the same. This approach here, it's a little bit non-standard in that I've only seen it in Kostic's paper, but it's all equivalent. It's all equivalent, and nobody's here to complain about it. The point is don't be surprised when you look at this, if you do go back to the paper and you see that this isn't quite the same. For example, you might say, well, wait, what happened to A2, right? In our work, let's go back to our work. You had this A2 here, minus 1 A2 over 3. But this is, the reason that's missing is this is actually tuned to a very specific polynomial. In particular, it's tuned to this polynomial right here, where A2 is minus 1. So he just slides that right in for you. And so you're not really going through the strict full-size cubic equation. And that's what I wanted to do for you. That's the level of depth, that's the extra level of depth I wanted to provide to this, is we're going to the core cubic equation, and then you can go back and you can see exactly how he derived this creature here. And like I said, this guy here is totally equivalent to our inverse cosine form, right, which was inverse cosine r over minus q cubed, r over square root of minus q cubed. If you start using, you need to prove the connection, you need to know the tangent of, I think you need to know the cosine of the inverse tangent, right? There's an expression for that. And I think that equals 1 over the square root of 1 plus x squared. Don't quote me on that one, but I'm pretty darn sure that the cosine of the inverse tangent is this or something very close to it. And I think you need the half angle or the double angle formula, which is what accounts ultimately for that too. I think it's the half angle formula that you need for the cosine. Anyway, the point is that the thing you find in Kostic's paper, right, in Kostic's great paper, is a little bit tuned to his specific problem, but it's still the cubic equation. And that's what this guy is. And nothing makes any sense unless you know that. So unless you know the cubic equation, you can start dealing with the roots, because everything about these orbits, everything about the analytical time-like geodesics in a Schwarzschild spacetime depends on the root structure of these expressions here. The root structure of this guy, and which is determined by the constants of the motion. The physics determines the expression, which determines the roots, and the roots determine the differential equations. All of these differential equations are characterized by the roots of these polynomials, and that determines the paths in spacetime. Okay, all right, so that's that. Okay, so to summarize what we've done so far, we know that we can take the physics and insert the physics into our problem through the constants of the motion. That would be kappa and h, and also the overall mass of the thing through the standard distance a, alpha. So with kappa, h, and alpha, we can construct in a Schwarzschild spacetime all of these essentially equivalent mathematical models of differential equation based mathematical models of what are we looking for? We're looking for the analytical time-like solution, time-like geodesics. Analytical means we're looking for a formula that gives us the answer of the path in space-time, and that is going to be a formula for x mu as some function of some parameter of the world line parameter, usually the proper time, as we'll see. So it's going to be x mu of the proper time tau. So these are going to be formulas. So in order to get those formulas, we have to solve these differential equations here, all of these differential equations. And we start by the physics, inserting the physics through the constants of the motion, the angular momentum, and the overall energy of our falling particle. And then we have all these equations to solve. We can solve, and different authors solve different equations. But in every single case, we're going to understand that in order to solve these differential equations, well, let's see, the physics goes in, creates the differential equation. Inevitably, they're always cubic equations, or the most relevant part is cubic. And therefore, the physics propagates into the roots of the cubic. And it's the roots of the cubic that tells us the nature of the orbits. And I think we talked about that in a previous lecture. So now we understand how to find the roots of any cubic. If the cubic has 3 real roots, we have this method. If the cubic has 1 real and some complex roots, we have the added step, at least the method I taught here, is the added step of reducing it to a depressed cubic using these formulas here, and then ultimately using these formulas here to find the roots of the depressed cubic. And then the final step is to go back from the depressed cubic to the original cubic. But you can also solve the problem in the depressed form, right? Because if you look at this, if you choose to work with this equation here from the beginning, then this is depressed, right? There's no u squared term. It's not fully depressed because you've got this 4 there, and it makes the transformation a little bit different. The transformation to depress that I taught here ends up having a 1/4 in it for the particular, it ends up having, we add a 1/4 term there to generate this guy, right? To generate this equation, right? If, in other words, the substitution chi from here, right? You start with this, and you make this substitution, you end up with this. Now, normally you would end up with, if you did the substitution I presented, you would have the same coefficient here leading here. But we want a 4 there because we want this to be the Weierstrass equation. So we added a 1/4 here, and it worked out just right. Anyway, that's a minor point. But the point is that this is where we are. We are now comfortable with the cubic equations. And the next thing we'll talk about is more mathematical foundation, because these guys are all going to be ultimately dealt with using elliptic integrals and elliptic functions. And there's just a whole ton of nomenclature to cover about that, and we'll do that in the next lecture.